Okay, welcome to session 1C on case studies and experiences. Our first talk will be by Yifan Yuan he's a research scientist at Intel Labs. He works on CXL memories and on-chip accelerators on Intel products. And today he's gonna talk to us about a quantitative analysis and guidelines of data streaming accelerator in modern Intel Xeon scalable processors. Take it away.
Should we just start now or just wait like a few more minutes here? You are still kind of. Okay, great.
Sorry.
Okay, great. Okay, hi everyone. Today I'm gonna talk about the Intel Data Streaming Accelerator or DSA, an on-chip accelerator on modern Intel Xeon CPUs for data transformation and movement. This is a joint work between Intel Labs and the University of Illinois. In modern data center, the data center and system tax has been increasingly a problem. It refers to the CPU cycle used for the fundamental infra and software routines, which could have been spent on the actual application and workloads. Identified by Google back to 2015, data center and system tags include but are not limited to memory movement, RPC, protobuf, hashing, and compression. To make things worse, there's been a tax inflation over the past decade. As disclosed by Google last year, in many scenarios, the tax rate surged significantly from around like 25% to more than 40%. As an attempt to reduce the critical data center task, data transformation, Intel has designed and implemented data streaming accelerator or DSA. DSA is an on-chip accelerator in the modern Intel Xeon CPU package and can do various data movement and transformation operations. DSA can provide high throughput with low latency for transformation operations and can be scaled to support many users. DSA is also user-friendly and can be even application transparent. So as a new IP on the modern Intel Xeon CPU, DSA has several unique features that facilitate its deployment and usage. The first one is its core accelerator communication. Software uses simple descriptors to submit the task to DSA, and this can be done by a new x86 instruction. The second one is virtualization and multi-tenant support. DSA supports shared virtual memory, meaning the software doesn't need to manage memory explicitly, such as painting a specific page. Also, multiple tenants can share the single DSA instance at the same time. Third, DSA supports processing the task in a batch. This reduces the task submission overhead. Last, DSA has rich QoS control support, from bandwidth provisioning to descriptor priority. This can be easily tuned by the software. Okay, so let's dive into the DSA hardware architecture. The front end of the DSA is a set of queues called work queue or WQ. They are responsible for receiving task descriptors from the CPU software. They are exposed to the system as MMIO registers or portals here, and the software can write descriptor to these portals, and the descriptor will be queued into the corresponding WQs here. The back end of DSA is a set of processing engine. There's an arbiter connecting the front end and back end for QoS purpose. And we can flexibly configure the WQs and engines into different groups. This is done via the out-of-band configuration interface. And we also have interface and structures for virtual to physical memory address translation, as well as the memory request. So here's the deeper explanation of the WQs. First is DWQ or dedicated WQ. It's intended to be used by a single client, which can be either a process or a VM. A user can use the new move64b instruction to write the descriptor to the MMIO region with low overhead. Also, the software needs to manage the queue occupancy, or say how many on-the-fly descriptors should be issued. On the other hand, we have the SWQ, or say shared WQ. Different from the DWQ, SWQ is intended to be used by many clients. The software can use the new enqueue command to write descriptor without explicitly managing the inter-client contention. The enqueue command instruction returns a status of whether the descriptor is accepted by the SWQ hardware or not. DSA exposed two programming models to the software user. So let's first see the pure software. In software, you have to issue instructions to load from or store to the memory, and then start the next task. So with DSA sync mode, like the CPU can simply submit the descriptor to DSA hardware, and while waiting for the DSA to complete the task, the CPU keep idle or just enter some like low power state. The CPU can move on to the next task upon the completion of the DSA task, which can be notified by interrupt or polling. With DSA asynchronous mode, after submitting the descriptor to the DSA hardware, the CPU can continue to work on the next task simultaneously. The next task can be software running on the CPU or another DSA descriptor to the DSA hardware. Regarding the software enablement, collaborating with the open source communities, we've built rich DSA ecosystem all the way from OS, VMM, libraries, frameworks to upper level applications. And here, I want to highlight two libraries that facilitate DSA's adoption in application. They are DML and DTO. DML stands for Data Mover Library. It provides a set of high-level APIs for the user, hiding the low-level DSA hardware details. DTO is DSA Transparent Offloading Library. It intercepts the default system functions like memory copy and replace them with the corresponding DSA functions adaptively. Users don't even need to recompile their program. Okay, so let's look at some performance numbers of DSA. These numbers are measured on the open source the DSA perf micro benchmark on an Intel 4th Gen Xeon CPU. For simplicity, we only show the memory move performance in this presentation. The first plot shows the throughput of a single DSA instance normalized to that of a single CPU core. As we can see here, as long as the data transfer size is not very small, DSA always has the notable throughput benefit over CPU cores, and this can lead to as high as 5 CPU core saving. Also, since more tasks are processed by the DSA hardware, operating DSA in asynchronous mode always provides more benefits, but this may require more software changes. Let's then see how DSA performance can scale with multiple instances on the same CPU package. As we can see here, the aggregate throughput scale almost linearly with the number of DSA instances. Note that in some extreme case, the DSA aggregate throughput is limited by the system memory bandwidth, and as more data is charged to the DRAM instead of DDI-O'd to the last level cache. Next, let's see how DSA can benefit CXL memory. CXL memory is an emerging technology that expands the memory capacity with secondary but slower memory tier. In this plot, we show the throughput of CPU and DSA for data transfer between the host DRAM and the CXL memory. In this case, DSA shows even larger benefit over CPU cores, showing its great potential in modern tiered memory system. This is because DSA is more latency tolerant, while the CPU core has to wait the outgoing memory request in their load and store queue, which can be easily saturated. That limits its parallelism here. And to learn more about DSA's architecture, performance, and software support, please see the paper for more details. Having all said, you may think, hey, this is cool, but how can I know I can benefit from DSA? I just don't want to get my hands dirty immediately. Well, that's a great question. And so here we suggest a step-by-step usage of DSA with little pain. First, you can try DTO that transparently offload the task to DSA for you. This is painless, and you just require a couple of configurations. Then, if you want more control and more benefit, you can consider the DML APIs in your code. And finally, if you really want to squeeze every cycle out of DSA, changing the programming model can be a good option for you. Then let's take a specific example to see how DSA with guidance can be adopted and benefit a real-world application. So here we choose the DPDK vhost, a VirtIO backend implementation for virtual network devices, and it's widely used in the software switch for VM. And DSA can be used for data movement between the VMs and the software virtual switch. So we have several guidance for the software developers. Some of them are about the program model and task size, and some are about the DSA hardware configurations, such as the engine and SWQ or DWQ usage. And some are about the right way to interact with the cache and memory hierarchy. So with those guidance applied in the DSA adoption to vHost, we see significant packet processing improvement compared to the CPU, where DSA can help process the packet with different size at a constant rate. So to conclude, Intel DSA is here in modern Intel Xeon processor to reduce the data center tax, providing strong performance and ease of use. This work provides a comprehensive introduction, performance characterization, and guidance of DSA usage. And we hope this can pave the way for broader adoption, more novel usage, and more research on DSA in the community. Thanks for your attention, and I'm happy to take questions.
Great talk. I'm Wan Wu from Peking University. So I have a question. If we offload some function to the hardware, there should be a limited number of the instance we can support. For example, the work queues. If the application want more instances than the hardware can support, how should we solve the problem? Or should we limit the programming model?
Okay, so I think it's more like the job of the system administrator, right? You have to configure like different number of like engines, right, on the work queues to different applications, and that can be done like via the kind of the system administrator. Yeah.
I think maybe we can add another virtual layer of virtualization to virtualize these work queues. Is that
well, yeah, that's definitely possible, and that's part of the job of the SWQ, the shared work queue. It doesn't limit the number of tenants you can have for that, like a single work queue.
Okay, thank you.
Hi, I'm Gonghan from Stanford. So I have a question on your page 12. So why the performance decrease when the transaction size is small?
You mean
slide 12? Yeah.
You mean this one, right?
Yes.
In which case, like
256 and 1K, the throughput decrease. Right?
Yeah. So that's basically why you're gonna like have the DSA only with the larger data sets, because like for DSA you need to like submit a task to your accelerator, and like the accelerator like do the things for you, and like you wait for the result, right? That's kind of some overhead compared to like doing everything on CPU core, right? So yeah, that's about like the granularity we're gonna offload. Yeah.
Oh, okay. Thank you.
You said something about DDIO. I didn't get it. Can you explain again?
Oh yeah, sure. Yeah. So for this part, right? Yeah. So typically you can, for DSA, you can choose the destination like data, whether you want to place it in like last level cache or just your DRAM. That's a kind of adaptive DPIO, right? And on the other hand, in this case, if you have really like fully utilized the 4 instance of that, like there could be some like data like stretched between the last level cache and the DRAM, and that will limit the bandwidth here. Yeah, we can discuss more detail offline. It's a little bit complicated here.
We have time for one more question, maybe. I was curious, so you said that there are 3 steps in which users could try it. What is the performance difference between if you use it sort of transparently versus you have the user optimize it?
You mean the steps, right? Like different like DTO or like more kind of code modification, right? Yeah, so it depends. So totally depends on your workload. Let's say for some like more straightforward workload like Redis or cache lib from Meta, and using like the DTO or like you don't need to really change anything and you can get significant benefits. But for more subtle usage, like you have to like think about like how to change your programming model. For example, in this case, right? In this vHost case, if you simply use the default transparent one, you won't see anything like beneficial. but you have to change the programming model here. Basically, in this case, we use the async model, which is high performance but require more like software effort.
Thank you.
Okay, thank you, everyone.
Next up, we have Mangpo. She's a research scientist at Google DeepMind, where she works on machine learning for machine learning compilers. She also has interests in sustainable computing. And today she's going to talk to us about synthesizing accurate counterfactual I/O traces from I/O samples.
All right, now it works. Okay, well, good morning, everyone. I will be presenting Thesios, which is a methodology to synthesize I/O traces from I/O samples. This project was started because a quest to answer this question. I am very curious to see if we can reduce energy consumed by this in our data centers. And the idea is fairly simple. If we can put all the code data into the same disk and then put those disks in low power mode, can we reduce energy in our data center? Well, to actually analyze this policy change, I want to do this in a way that it's actually evaluate on realistic workloads. This motivated us to build a tool and a methodology to synthesize representative I/O traces because these traces are very critical to the designs of storage system. It can help us understand the behavior of the current system and also analyze proposed changes on various different metrics, for example, latency, power consumption. This methodology can also enable industry to share realistic traces from large-scale data centers with academia and vendors for them to work on optimizing workloads that are the realistic workloads that industry actually cares about. So our idea is to leverage sample I/O disk traces because I/O samples are routinely collected by distributed storage system in large-scale data centers. In particular, we typically have telemetry system or sampling system that collect some of the I/O samples. For example, this system might collect 1 every n RPCs that go to the storage server. The downside of analyzing or looking at just the sample traces is that there are a lot of things that we cannot really get from them. For example, we cannot get I/O requests into arrival time, or we cannot try to evaluate changes such as data placement policy changes, or what is the effect if we use new hardware in our data center. So we built Thesios, which is a methodology that will allow us to synthesize I/O traces that are both representative, that can capture the current workloads that we have in our data center, but also able to synthesize counterfactual traces that will enable us to perform various what-if analyses. And the key idea is to combine I/O samples from multiple disks to make up or synthesize a full resolution trace for a single disk. Here's the overview of the framework. The first component is the sampling service. In this work, we simply leveraging an existing sampling service that we already have in our data center. In particular, we choose the sampling mode where the system collect all of the requests that goes to 1 every n files. So when we have these samples, we need to think about, okay, which samples from which disk we want to combine to make up that one full resolution trace. Now, if you look at this in even the same data center or same storage cluster, this might experience very different I/O activities and behavior. So if you combine samples from disks that have very different experience together, you might not get a representative trace for any disk in the data center. To do this, we have an identity identifier that identifies similar disks by running k-mean clustering on various features that capture both disk and trace characteristics. So now that we identify similar disks, which is in the same k-mean cluster, we need to figure out how many samples we actually need to combine to make up a full resolution trace. This is actually quite simple. So if the sampling service sample 1 every n, or like have 1 over n sampling rate, we essentially need to combine samples from n disks together. At this stage, when we have the combined disk trace, this actually represents the trace at the server level. To get the disk level trace, we need to do a little bit more reorganization. What do I mean by this? If you look at what happened in the storage server, it does multiple things. One of the important things it does is that it may reorder requests according to the priority of the request, which means that the order of the request observed by the disk might not be the same as the server. So we have to take care of this. Second, server has a buffer cache, meaning that some of the reads may be served from the buffer cache and only misses will get forwarded to the disk. Third, all of the writes operation will first get written to the buffer cache, and eventually it will get written to the disk in a batch at a later time. So we built a minimalistic server simulator that captured these behavior in order to synthesize the disk arrival time of the request, the end-to-end latency of the request based on the ordering and the queuing. So now that we have all of these necessary components, let's take a look at how accurate the synthesized traces are. To do this, we run an experiment by comparing the aggregated statistics that analyzed from the synthesized trace compared with the realistic or ground truth that we collect from the telemetry system. Here I show you a few metrics that we evaluated on. So I show here a number of disk reads and also writes across different days in a week and also across different hours in a day. You can see that the result from the synthesized trace actually matched the reality quite nicely. It's able to capture the fluctuation of reads and writes across multiple days and also across multiple hours. Next, let's take a look at how we can use Thesios to perform counterfactual analysis. So Thesios can synthesize representative I/O trace, as already shown in a previous slide. We can also extend Thesios to synthesize counterfactual trace. To do so, we extend Thesios to synthesize a trace for a disk with a specific capacity, fullness, and utilization. For example, synthesizing a trace for a larger disk that maybe we don't have in our data center. Second, we also support synthesizing for data placement policy change. To do so, we need to be able to synthesize a trace for a disk that may contain only files that meet a specific filtering criteria. We support filtering criteria by application, age, and encoding. Once you have a trace, we can then analyze the trace using various methods. For example, feeding it to a simulator or an emulator that actually run in the real environment, meaning that running real server binary and also run on the real disk. So in the counterfactual analysis, we can also easily extend our simulator to model changes, including new types of disks and also hypothetical disk power management. For example, spinning down the disk into low power mode. We can also extend our simulator or change our simulator to experiment with new configurations. For example, a different cache policy or changing the size of the buffer cache. Now let's take a look at a few interesting case studies that we use Thesios for. So this first case study goes back to the original question of, can we reduce energy consumption if we segregate hot and cold data, put the cold data on the same disk and then powering that disk down, right? So to do this, we have to be able to basically model the data placement policy change. So we use the filtering feature of Thesios to basically synthesize a trace for a disk that contain files that meet a specific filtering criteria in order to make up the cold or the hot disk, right? Now, typically we would combine n disk traces to make up a full resolution trace. With this filtering feature, let's say that F is a fraction of files that meet that filtering criteria. So in this case, we essentially have to combine 1 over F times more traces to make up for the full resolution trace. In this experiment, we use age as a filtering criteria. So only include files that are older than certain age into the cold disk, right? And we varying the age threshold on the x-axis. As you can see, by doing this, when the disk contain older and older files, mean the disk get colder and colder. We are able to reduce the utilization of the read time within a day from 52% to 8% and increase the inter-arrival time significantly. Unfortunately, this is not quite enough for putting the disk into the low power mode, because if you look at the inter-arrival times, even though we increase that significantly, it's still quite small. So there's not enough time to actually powering it down and up to be ready for the next request. In particular, for the current workload that we have and on this particular data center. So let's take a look at slightly different strategy. What if we use a low RPM disk to save energy? To do so, we have to modify our simulator to model the low RPM disk. The main part is that we have to model the disk time. This time consists of 3 components: seek time, rotational latency, and transfer time. The speed of the disk affects rotational latency and transfer time. So what we do is that we essentially scale these 2 components linearly according to the speed of the disk. We validate that our synthesized disk time is actually accurate by comparing with the real disk time evaluating on the low RPM disk, the real disk. Once we found that this is actually quite accurate, we then use our simulator to analyze the end-to-end latency of all of the I/O requests in the representative I/O traces. And as you can see, if we use low RPM disk, the latency does go up, but actually not by a whole lot. And in fact, this latency is actually well below reasonable SLO. But if you're looking at that average power, it's get reduced significantly between 20 to 30%. So the strategy of using low RPM disk seems to be quite promising in terms of reducing energy consumption in data center. In summary, I show you Thesios, a methodology to synthesize representative I/O traces, but also can be used to synthesize counterfactual traces to perform various what-if analysis. I show you 2 case studies, but there are a few more in the paper. And last but not least, we are very excited to announce that we are also releasing 2-month-long synthesized trace using this methodology along with our paper from 3 different Google storage clusters. 1 day of trace have about 5 to 10 million records. So it's a pretty large scale data set. And with that, I am, thank you for listening, and I'm happy to take questions.
A very basic question. The slide before when you showed the low RPM data. So if I look at the L95, so it's like 39 to 66. So how do you, so you said it's not a significant increase on latency, but how do you quantify that? If you look at percentage or just below an absolute threshold?
Yeah, so like within, different data center, we have our own like SLO threshold, and I cannot reveal what's the exact number is, but I can only say that like the L95 for even like the 42,000 RPM is actually still below like our threshold. Yeah.
Thank you for the great presentation. I would like to know what are your thoughts if we were to replace rotational disk with something like SSDs, which have different latency and performance trade-off for read and write operations.
Yeah, so I'm not the expert in like this or like storage system, but I think that this characteristic might work. There's a definitely trade-off, as you say, right? And depending on the types of workloads, maybe one types of disk would have better power or like performance characteristic for that particular workload. So I think the key takeaway is that I think it's very important to be able to actually have like a realistic workloads that we care about and actually like use that to inform the design, whether what kind of disk we want to use in our data center.
Thank you.
Yeah.
We have time for maybe one more question.
I have a question. So how do you achieve that high accuracy? Do you need to do calibration between your simulator and the real latency of disk? So when you are modeling the disk, do you get it from the spike of the disk, or you measure and calibrate with your simulator system?
Yeah, for this particular experiment, we actually don't have to calibrate anything. So it's basically just from our intuition that, okay, this time have these three components, and then the last two components need to be scaled based on the speed. And I think there's a little bit of tuning in a sense that we also, for some of the requests that go to the disk, sometimes it's actually hit like the on-device cache, which is like on the disk. And for that, you don't actually need to like rotate the disk because it's hit into the cache, right?
Yes.
So we need to be able to characterize which request will hit the cache and which request will actually need to like rotate the disk, right? And once we take that into account, it's actually pretty simple by just like scaling these two components.
Oh, okay.
Yeah.
Thank you.
Let's thank the speaker. Next, we have Michael, who's a PhD student at the University of Wisconsin at Madison. And his research interests are in AI accelerators. And today he's going to tell us about a journey of 1,000 kernels begins with a single step, a retrospective of deep learning on GPUs.
Hopefully it shows up. It's on duplicate, but it's not showing. Oh, okay. Important. Try it for a dongle. Anything? I can send you a link to these slides and pull it up there, or oh, I can connect. There's a problem with your laptop. Could you connect again? Maybe I'll present it from my phone. Well, let's see here. This is fine. I don't know if this will work. Maybe. That's funny. If I do that, does that work? It's on to external display. Usually because your sorry? They're going to check it now. I mean, I can just do it on my phone here, if that works. All right, some technical difficulties. A good way to start it off. Hi, I'm Michael Davies, and I'll be giving a talk about my paper titled "A Journey of 1,000 Kernels Begins with a Single Step: A Retrospective of Deep Learning on GPUs." We're going for something concise and catchy with this title. So, being a case study, let's see how this works. We wanted to look at how the AI revolution has panned out for deep learning hardware. And we observed that the MLPerf benchmark suite, which is sort of the standard benchmark suite for machine learning, doesn't have a lot of diversity in its applications. So it uses a lot of convolution networks. It includes transformers and also throws in like RNNT, which is an LSTM network. And we wanted to study we wanted to answer three questions in the context of this, in the context of contemporary deep learning applications. The first is, how does deep learning application behavior scale across hardware generation? The second is, what are the software compiler and hardware interactions responsible for this? And the third is, what can we learn about where architecture evolution should focus? So on the right hand of this slide, you can see sort of our methodology. We ended up narrowing our study to look at just NVIDIA GPUs, which are currently the dominant platform for AI. And so we looked at 3 generations of NVIDIA GPUs. We looked at Pascal, Volta, and Ampere. And then after that, we came up with an application set based primarily on citation count and diversity of use case. We call this the Casio benchmark suite. And then we also threw in GPT-3, and we studied ResNet and BERT throughout our paper as well. So you'll see those 3 pop up, but those aren't canonically part of our benchmark suite. So the first thing that we did is we looked at sort of the software perspective of how these applications run from the perspective of the framework, what are the operators that are in these applications, and what are the CUDA kernels that execute on the device. So we looked at a breakdown of the operators in these applications. So this table here shows the runtime breakdown of the top 4 to 5 framework level operators for each application. We also collect statistics on the number of device kernels or CUDA kernels that executed in each of these applications. And the main observations here is that most applications spend about 80% of the runtime in just 2 to 10 framework level operations. And there's roughly 20 to 80 unique ops per application, with a cumulative total unique of 185 framework level operations. And we see that for Ampere, for example, there's a total of 744 unique device kernels that are executed. And concerning GEM in particular, we have something in the range of like 100 to 300 CUDA kernels that just implement GEM or matrix multiply operations. And speaking of GEM in particular, one thing that I want to note is that over GPU generation, we notice that the percentage of runtime that goes to GEM is actually decreasing. And this is mostly a consequence of Volta introducing the tensor core and increasing the tensor peak compute by, I think, a factor of 8 or so in that range. And so we see this geomean of 50% runtime in Pascal go down to about 35% for Volta and Ampere. And so that brings us to our first set of insights that we got from our study. The first is that there's a heavy tail of operators in device kernels that a deep learning architecture must support. And the compiler, architecture, and microarchitecture bear the responsibility to create and execute performant code. The second insight is that in addition to the first, each operator might have many device kernels that are specialized to certain aspects of the operator semantics. So think like those specialized kernels for GEM. There's many shape specialized kernels for these operators. And then the third insight is that the lower contribution of GEM-based operations on newer GPU hardware and the likely lower future generational improvements of GEM performance suggests that this era of GEM acceleration is over. So the next thing we did is we looked at sort of the hardware perspective. And so we did this application-informed hardware analysis. So now we're looking at how do these applications actually execute on the hardware. We're looking at performance counter data and how they look like to the GPU. And so the first thing we did is we collected a sort of a timeline of utilization. And so on the bottom right-hand corner of this slide, you can see for a couple of our applications, we plot on the x-axis is sort of the fraction of runtime, and the y-axis is the utilization of different resources. And we order the kernels on the x-axis by increasing utilization of the SM, which is the streaming multiprocessor in the GPU. And then for DRAM and tensor utilization, we do a sort of an interesting cumulative average, where any point on the x-axis, if you take 0 to that point, and you take the average of DRAM utilization and tensor utilization for that interval, that's where the y point is. And so what these charts let us see is the maximum SM utilization for some fraction of runtime, and then the average DRAM and tensor utilization for some fraction of runtime. The next thing we looked at is sort of this sort of classification of execution states, where we took the dynamic execution behavior of each kernel, and we classified it based off of how much parallelism it has, which is based on the number of threads, how much it uses the SM, so SM utilization, and then how much it uses memory bandwidth. And for each of these features, we classified it into a low, medium, and high. And so we ended up with 27 sort of execution states that a kernel can fall into. And we lumped together these L states together. And on the top here of this slide, you can see a stylized timeline of each application that shows, what execution state is it in at any particular time. And then on the right-hand side, we sorted all of the same bins together. So you can see sort of this fractional breakdown of the execution states. And then finally, and I realize now this actually shows up kind of small on the screen, this is sort of the poster child figure for our paper, which is the generational speedups of our application suite for the Volta over Pascal and the Ampere over Volta speedups. And then we also throw in ResNet, BERT, and GPT-3 from MLPerf, and then GPT-3 is a large language model. So the observations here are that the majority of applications, most of the applications spend a majority of their runtime with less than 25% utilization of any resource. And the second is that there's a lot of diverse execution behavior, and this execution behavior is changing quite rapidly. These little numbers that are in parentheses here on the timeline charts, which is a little hard to read, show the average run length in terms of number of kernels for each execution state. And then the third observation is that we see Volta gets about 2.4x geomean of Pascal speed up, and Ampere only gets about 1.1x Volta, despite doubling the peak tensor performance, by the way. The next thing I want to do is, from the hardware perspective, dive into gems specifically a little bit. And so what we did here is we took our application suite and we extracted out all the gem shapes that are executed in these applications. And before I get into the results, I want to talk about this figure on the bottom here, which is a depiction of the standard tiling strategy for a gem on an NVIDIA GPU. This is adopted from the documentation for NVIDIA Cutlass, if anyone's familiar with that. And so what we did is we conducted a couple experiments where we basically extracted out the performance of each gem shape. And on the top here, you can see a histogram of the peak compute utilization for the gem shapes on Pascal, Volta, and Ampere. And then this middle chart shows basically a plot of the peak tensor utilization versus arithmetic intensity, which is measured in flops per byte. And then we also included a sweep of gems, which are these colored dots on this plot as well. And then finally, in the bottom right-hand corner, you can see a selection, a subset of gems that we included in our paper, which are a subset of the application suite that we have. And the main observations and insights here is that there's a lot of shape diversity. And we also notice that performance is improving. In our table here, you can see Volta gets about 2x geomean Pascal, and Ampere gets about, 1.6x Volta. But despite performance improving, we see that utilization is actually getting worse. And that's likely because there's a lot more compute available, and it's getting harder and harder to actually realize all of that compute. And then we also noticed that arithmetic intensity does correlate with utilization. And that kind of makes sense because arithmetic intensity kind of is a proxy for how much reuse is available in the gem. And we also noticed that you need large dimensions for the gem on MN and K to get really high utilization. We noticed that for NVIDIA GPUs in particular, M and N are used primarily for parallelism, and the K dimension is used for that inner loop to exploit output reuse. So that brings us to our fourth and fifth insight. The fourth insight is that there's substantial underutilization of all hardware resources, and this provides an avenue to target for future speedups. One caveat that I want to point out is that transformer models do get high utilization on GPUs today, and this is mostly because they have very large matrix multiply dimensions, which have very high arithmetic intensity. And our fifth insight is that there's a lot of diversity and temporal variation of execution state, and this suggests that hardware features must be able to support rapidly changing execution behavior. So that brings us to sort of the final part of our paper, which is sort of a forward-looking, what can we do with this information? And so what we did is we developed, or we studied three interrelated composable behaviors for this post-gem era. The first is data orchestration, and this concerns how data moves from the DRAM or HBM on chip and through the memory system. The second is compute orchestration, which concerns how compute is actually carried out by the processing elements, so the SM, the tensor core. And then the third is dependence orchestration. So in these AI applications, you have this inter-operator parallelism that's exposed through this graph structure, and that is sort of this third behavior. And so we find that targeting all of these behaviors is really needed to provide really good speed up for future AI accelerators. And so what we did is we looked at all of our applications, but for example, here I have a subset of an application called mesh graph nets. And I've broken it down into how much runtime is spent in different operators in mesh graph nets. So you can see like 21% of runtime is spent in linear layers, about 15% in these scatter operations. And based on these operations semantics, we classified them as data dependence or data orchestration heavy or compute orchestration heavy. And we were able to very simply model what would happen if we increase the data orchestration or compute orchestration of a AI accelerator by 2x. And then for dependence orchestration, we sort of assume that there's some magical way that we can, and this is a forward-looking model, by the way. So we assume that there's oh, am I running out of time? Oh, okay. So it's 13 minutes here. Okay. Anyway, so this chart shows basically what are the opportunities. And if you do 2x everything, we get a good opportunity for future AI accelerators. So that's actually my last slide. I want to thank everyone for their time and happy to answer any questions.
Hello, thank you for the great talk.
Mm-hmm.
Thank you for the great talk. Do you consider the impact of number formats in this study? Because these different GPUs support different number formats.
I'm sorry, can you repeat the question? I didn't quite.
Because these three different generations of GPUs support different number formats, do you consider their impact on this study?
Oh, are you talking about data type, like
different type of floating
I
point,
see.
yeah.
So for this study, we actually focus on FP16 exclusively. We find that the original inclusion of the tensor core and Volta used FP16, and so that's why we ended up using that data type. And for other data types like int8 or int4, at least for NVIDIA GPUs, it's a straight 2x, 4x peak compute improvement. And based off of data sort of density, we assume that sort of the data type roughly correlates to just a straight linear performance improvement.
Okay, thank you.
Yeah.
Running out of time, so maybe we can do the other questions offline.
Okay, sure.
Yeah, thanks. Okay, while Leonardo is setting up, let me introduce him. Next up is Leonardo from Meta. He's a performance and capacity engineer at Meta, and his research interests are in power management in the data center and more generally.
Hello, everybody. I'm Leonardo. I'm a performance and capacity engineer at Meta, and good afternoon, all. Today, I'm going to explain our work expanding data center capacity with DVFS boosting, a safe and scalable deployment experience. So the context of this work is COVID-19. When COVID-19 hit, we saw unprecedented demand increase in our infrastructure. For example, in countries that were in lockdown, we saw about 50% in message increasing and more than 2x in voice call. So this put a lot of pressure in our infrastructure, and we need to reply really quick to maintain a good usability to our users. So in general, we can have many different ways to expand capacity, like from top right, we can build up new data centers and put extra machines there, but that would take years to do. Other things that we can do is to buy new servers, but during COVID, the supply chain was all disrupted and we are not getting servers quick enough. Then we can do application software optimizations, or we can do things like hardware configuration, which is like DVFS boosting. So in this particular case, in this particular talk, we focus on DVFS boosting. We did some others of these techniques during COVID, but this talk is just DVFS boosting. So to understand DVFS boosting is like we increase the CPU frequencies of the processors, but then this can increase the power consumption of those. So our infrastructure is limited in power, so we need to attack the power cap risks on that. So what is a power cap? A power cap is when the power device is consuming more power than the limit. Like in this case, we show this hierarchy of our power distribution. We have 3 levels that we control power. We have the main switchboard, the switchboards, and the panels. So they have different power limits, and we need to respect that. If the machines underneath start consuming more power, we have to reduce the frequency or the power limits of these machines, and that's a power cap, which has impact into the capacity, right? So we need to manage this really well. So the main sources of power capping is imbalance in our infrastructure. For example, some switchboards can have 8 panels, or some others can have 7 panels, and this causes some heterogeneity. We also have heterogeneity into the hardware placement, which can also cause imbalance. Like some panels can have a different type of racks that consume more power than the other. So then we can have some risks of power capping. The same thing for software placement. We try to be very homogeneous at the main switchboard level, but at the finer grain, it's very hard to do. And on top of that, DVFS boosting put extra risk into power capping. So we need to do an abstraction. So very quickly, we have this abstraction layer on the power capping. It can be local and transient, which is very easy to do, and we treat as a random failure as a hardware, or it can be like persistent and local, which is like we do rack moves. We ask our facility to do rack moves. Can be regional and transient, where we can allocate some capacity that's going to be used just by low priority, and we can shut down or power cap these machines without compromising our infrastructure, and can be regional and persistent. This one, we don't want to use that, and for the DVFS case, we pretty much don't enable in a region if we see this risk. With this framework, we can reduce, like in this figure, we compare 2 years of 2020 and 2022. So we can see that we could reduce the risk of power capping. So now that we know how to manage power cap risks, let's come back to DVFS boosting. So we have service heterogeneity, which is like, what is the main bottleneck of the services? Some services use a lot of CPU and they are bottlenecked by CPU utilizations, others memory capacity or I/O. So in general, DVFS boost helps on the CPU utilization workloads, but we also have some use cases in the paper that we show that even I/O capacity, DVFS boost helps to reduce the latencies. And we also have services running on the same server type, but the different generations. So these also, like as more modern the CPU are, the better the power management are. So they consume less power. So there is some effect, different effect into the DVFS boosting effect. So we have thousands of services to choose. One can think of, hey, we can do just some A/B tests and choose which ones are going to behave better and get your better performance. But that's not right for our long tail services. For the big ones, that's true. But for the long tail ones, we don't have a good infrastructure to do experimentation. And during COVID, we didn't even have capacity to do these experiments on the fly. So some of those even have a lack of application performance metrics, and we have to come up with some proxy measurements. So that's our general framework that we have. We had the foundational work there where we have telemetry services that collect performance counters and provide some configuration, some counters for our machine learning heuristic to decide which workloads we want to do. And then we pretty much manage the power capping risk with a comment, and then we roll out this through our infrastructure. I'm going to details on each of those. So the telemetry service, we have on every single server in Meta, we have this service running and collecting performance counters like microarchitecture performance counter, power, and application-specific metrics. And we also have this metric that we derive its throughput useful MIPS, which is a proxy for the application performance in case we don't have that. So with this data, we put in our machine learning, we have applications that run, we're running with turbo or DVFS boosting enabled or disabled. And we build this candidate selection based on this data that we have, and then we could attack the long tail services. So we use the multivariate adaptive regression spline classifier. They can help us to capture the non-linearity, and we have 3 classes. Class has high performance per watt if you enable DVFS boosting medium or low. And then these all based on the large services that have applications and A/B tests. So we collect this, build this infrastructure. We provide 28 counters there, and the Mars select 8 counters for us to figure out the applications to run. Some model insights. We can abstract the performance of an application as computing time and memory accessing time. So some of the signals that we saw that the machine learning capture is like, for example, IPC. Applications with high IPC usually are high intensive computing, and that can benefit from DVFS boosting. Some that are more accessing memory cannot benefit much. So we can see the distribution of the benefit of DVFS boosting for the applications that we enabled here. And we see that it ranges from like 2-3% to even super linear, like 50%, but on like mean, it's around 25-ish%. So that's our power sufficiency framework, because as I mentioned, we have to figure out if this is going to cause extra power capping and wash it out our benefits. So we have this model where we know our fleet layout, and we build based on the candidate heuristic, we build a list of services that we want to enable DVFS boosting, and we also provide a power override. In general, our rule of thumb is that DVFS boost increase power by about 20%. So we pretty much combine these things, and now we have a new configuration of the fleet. Based on this new configuration, we know the hierarchy of our power distribution, and we figured out which ones are going to have more risks of power capping, which is we call like power overages. If there is some power overages, we mitigate from the techniques that I commented before. So then we need to make sure this is going to actually work. So we roll out in a single region, and then we compare the results. And we pretty much validate if this is going to benefit or not. And if it benefits, we capture this and propagate to other regions. And if not, we just reverse. So overall, in terms of our results, this could create about 12 megawatts of extra capacity, which equivalent as half of data center in Meta populated with servers. So pretty much is like we were building half of a data center, which helped with the capacity crunch. So that's all for now. There's one more details in the paper. Studies on each of the applications, and I invite you to take a look. Thank you so much.
Hello, great talk, Bura from EPFL. So I wanted to ask you if you considered the underclocking of memory-intensive applications while boosting the others.
Yeah, that is one. We need to keep this infrastructure simple. Like we have these thousands of services, and if we fine-tune very well for a specific service, it's really hard for us to do at scale. We were looking at investigating other knobs like data fabric frequencies and some of those, but this complicates a lot for the service owners. They don't know how to use those things. And once you come to them to propose this, they also say, hey, what's going to be impact of my application? So there is like some human interaction on that. So we try to be very simple. So then people reduce the adoption barrier from the service owners that don't know much about computer architecture or power.
Okay, thank you very much.
Hi, Matt Sinclair, University of Wisconsin. Really, really interesting talk. I'm curious, there's been some work by, one of your colleagues at Meta who's, sitting to the right of me that's observed that, CPU servers have significant variability, like performance variability under the hood already, just from manufacturing defects or whatever. Do you have a sense of how that impacts your finding, like when you want to boost or when you don't want to boost, or if ignoring that is okay?
Yeah, so that was one of the concerns. We had some service that had, like when I proposed, it took like 1.5 years for me to convince them to do, because they say, hey, you're going to cause us performance variability. And suddenly like using this approach, I say, hey, I'm going to flip on region for you. And you tell me what's going to happen. And I flip the region for them and they say, hey, nothing happened. So we are good. So yes, it can cause, but we have some other overheads in our software stack that cause performance variability as well. So from our experience, it didn't increase this, but for sure there is a human resistance about this because they have the perception, but once they see the results, it's just like an impression, but yes.
Okay, may I ask one more question? Sure. Can you give a little bit more intuition about your classifier? So I understand you have, all these hardware counters and you're binning it into high, medium, and low amenability to DVFS boosting, but can you give us a sense of like, what does it mean to be high versus medium?
Yeah, so that's what I try to capture in this picture here. So pretty much high are the ones with very high IPC, which is a good indication of that you are spending a lot of your time into the compute, not waiting too much memory. We saw that for the low is when you have like high memory bandwidth or high L3 cache misses. And medium is some combination of both. So it's pretty much if you are very, very intensive in memory bandwidth or using a lot of memory, it's pretty much the low because high frequency is just not helping at all.
Thanks.
Okay, let's thank the speaker. Thanks everyone for attending. Enjoy lunch.